All right, well, thanks for coming, everybody. As Russ mentioned, there's a lot of logos on this slide, and I've had the really great pleasure of working with a lot of people on this project. It's been a fantastic experience. So today I'm going to tell you about a really interesting polymer system that I've been studying over the last year under REACT, in which we have these sub-nanometer lamellar ion channels that self-assemble in this polymer. So I, of course, am part of REACT. REACT has 3 components, and I'm working in the 3rd component here, which is self-assembled nanomaterials for energy generation and storage. Fuel cells have the potential to really drive the next energy revolution, the so-called hydrogen economy. So one example of that is that we could store energy from intermittent renewable sources as hydrogen, which could then be used in a whole variety of applications, including electric vehicles, which use fuel cells to convert hydrogen into electricity. So a fuel cell, as I mentioned, takes in hydrogen, and the hydrogen reacts with oxygen to produce water and electricity. And the component of the fuel cell that I'm going to be talking about today is the solid polymer electrolyte membrane here, which is responsible for transporting these protons over to the cathode where it reacts with the oxygen. And so, so this is really a critical component of the fuel cell. And Nafion has been the industry standard for this membrane for around 40 years, which is kind of amazing. But Nafion has this disordered morphology, as you can see here, with these hydrophilic domains which contain water, and those are responsible for transporting the protons through the membrane. Meanwhile, these hydrophobic domains, which contain crystallites, are responsible for the mechanical integrity. This is the chemical structure here. It's a it's a random copolymer with hydrophobic backbone and hydrophilic side chains terminated by sulfonic acid groups. And so Nafion has some great aspects, which is why it's used so widely, but we'd also like to improve on these parts of Nafion, and so that's what this work is mostly about. We have a new structure, which we think of as really a new strategy for designing these membranes. So we're going from this disordered morphology to a highly ordered, layered morphology. And being highly ordered, that means that we can really understand it in detail. And we can also, it's also going to be tunable. Okay, so how did this project come about? I did some work previously studying this polymer here. This is a linear polyethylene with carboxylic acid groups on every 21st carbon, exactly every 21st carbon. And previous work that I did showed that this polymer crystallizes in this kind of, this way. So the chains are actually folded, forming this multi-layered morphology. So we thought maybe this structure could be useful for proton transport if we replace this functional group with something more appropriate. So thanks to the Wagner Research Group, who we collaborate with, we have this new polymer with sulfonic acid groups every 21st carbon. And through X-ray scattering, I showed that this forms similar kinds of layers, where you have these layers of sulfonic acid groups containing some water, and the layer spacing is around 28 angstroms in the dry state, relatively dry, that is. So this is looking promising. Maybe these layers could actually convey protons. Maybe protons could make their way through these layers efficiently, and that could be really good for a proton conducting membrane. And indeed, the conductivity is really very promising. At high humidities, we have conductivity exceeding that of Nafion. And we have a very steep dependence on the humidity. So in other words, on the water content of the membrane. And this high conductivity is especially remarkable given that being a hydrocarbon, our polymer is a weaker acid than Nafion, which is a fluorocarbon. So this is promising. Let's look more closely into this layered structure and understand it in more detail. Experiments at Grenoble that I did this past summer showed that these layers can be swelled with water simply by increasing the humidity of the environment around the membrane. And this is actually reversible. So if we remove the humidity, the water leaves the membrane, leaves these layers, and this shifting of the X-ray scattering peak here shows the changing of the layer spacing here. So we're going from 28 to about 31 angstroms. Looking into this a little more closely, I've plotted here, I've obtained the layer spacing from X-ray scattering. And I've also obtained the hydration number, also from experiments done at Grenoble this summer, where by changing the humidity, we're basically measuring the mass of the membrane as a function of humidity to obtain the number of water molecules per sulfonic acid group at each particular humidity. And so with those two data sets, I can combine them and make this plot where you see a linear dependence of the layer spacing on the number of water molecules, which makes sense for a lamellar structure. Okay, so how well do we really understand this structure, the polymer conformations, etc.? I've done atomistic molecular dynamics simulations to really take a look at where the atoms are in this structure. And so here is the polymer, and so you can see that the chains are folded and the sulfonic acid groups are here, located at the chain folds. And the results of these simulations, after relaxing the molecules into a low energy configuration, we obtain a layer spacing that really agrees well with experiment. So that's pretty cool, and that says that we really understand the structure well. And so I think this is really opening the door for more probing of this structure, perhaps even using quantum mechanical simulations to look at the water dynamics in the layers, and really getting a handle on that, understanding that well. So what are the next steps here? The next thing we really need to do is understand the semicrystalline morphology and how that relates to the conductivity. So obviously this is not a single crystal system. We have grain boundaries, and we probably have amorphous regions of the polymer. But we need to understand that structure better, and we need to understand how that relates to the conductivity. So for example, our protons in our conductivity measurements are protons moving through a layer and then kind of making their way through an amorphous domain to get to the next layer. So we need to understand how the degree of crystallinity is going to affect the conductivity. For example, we can reduce the degree of crystallinity by quenching the system from the melt. We also need to understand the crystallite size, and by that I mean the overall size of one of these crystals. What's the thickness in this dimension? What's the overall size here? And how does that affect the conductivity? And can we grow crystals that are large enough that we could probe the conductivity of a proton only inside the crystal so that the grain boundaries are not really playing an important role anymore? So I think that will be a really critical piece of understanding how protons are moving through this interesting new structure and how that might be used for future membrane technology. To understand this, I plan to do in situ Sachs measurements as a function of temperature, humidity, crystallization condition, etc., to really get a handle on the structure at this length scale. So to summarize, we have a new highly ordered layer structure with effective proton transport. And we think that this could really be a new strategy for designing proton conducting membranes. They're very different from the typical disordered random copolymer structures that are industrially used today. Thank you, and I'll take any questions.
I have a question concerning the molecular dynamics that you mentioned. How was it done?
The simulations?
Yeah.
So those were, they're atomistic simulations. So all the atoms are represented, but there's no quantum mechanics represented. And so the way I did those simulations was to build the molecules in a particular kind of guess starting configuration, and then relax them and see where they relax to and what that resulting structure is.
I was wondering if you could comment on perhaps the relative resistances to proton transport from the sort of nice continuous H-phase phases that you make and the disordered regions. So I have one, and in particular, you might come up with a relative order of magnitude as based on comparing to significantly more ordered things like carbon nanotubes and proton transport to carbon nanotubes, for which people have both simulations and experiments.
So you're wondering?
I was just curious if in your system, if the resistance to proton transport is being dominated by one or the other, your path, your ordered path, or the disordered paths that you might have to traverse.
Yeah, I think that's a really critical question. That's what these future experiments are going to try and get at. Because you're right that I haven't. I mean, it's a really important question. What's the role of the different phases? What's the role of the grain boundary as well? Sorry, I don't have a very satisfying answer right now, but hopefully soon.
So my question is related. You showed one plot where you compare the conductivity of this polymer to that of Nafion. So what was the crystallinity of that particular system?
Of my system?
Yeah, there was one plot.
Yeah.
I think, right? Where you showed conductivity as a function of relative humidity.
Yeah.
The two polymer system. One was Nafion, and the other one was, I think, the precise polymer that you have. So do you know what the crystallinity of your sample was?
It's difficult to know the crystallinity because we don't know the enthalpy of melting of this system, of this polymer. So I've done a little bit of I've done basically one experiment using an in situ X-ray method where you start with a completely melted polymer and assuming that you keep the thickness constant and that the X-ray intensity is constant. As you cool down the polymer, you can look at the absolute integrated peak intensities. And so I've done that for one case, and I've obtained a crystallinity of roughly 40% with that method. The issue with that method, though, is that this is using the wide-angle crystalline peak. But if you look at the structure here, there's a lot there that's not going to give you a diffraction peak, right? The water, the chain folds. So I'm not completely convinced that it's 40%. It could be significantly higher.
We still have time for questions.
What's the shortest length of the hydrophobic spacer that you could use to get a stable mechanical membrane? Because all that hydrophobic stuff is you're losing flux, right? So you want to minimize the hydrophobic part that's excluding water. What's the lowest molecular weight you could think between acid groups?
So for the sulfonic acid polymer, we only have, the only other one we have is a 9-carbon spacer, which is too short to form these layered structures. In our other polymers, we've seen that the 15-carbon spacer sometimes does and sometimes doesn't form these layers depending on the functional group. So that'd be interesting to look at the 15 spacer with the sulfonic acid, maybe a 17. I would guess that somewhere in there you would start to get these structures. This is a 21.
Any last question? Okay, that's that.